Hi everyone, welcome back. We're going to continue our discussion of trees, and also we'll get into rooted trees. So let's remind ourselves that a tree is a connected multigraph that does not contain a cycle. So we need these two conditions. It's got to be connected, and it has to not contain a cycle. If it satisfies those two properties, it's what we call a tree. Last day we found there was a couple of main properties that trees had. One of them was the number of vertices is exactly one more than the number of edges. Or another way to say that is the number of edges is exactly one less than the number of vertices. This is something that I remember based on the fact that a path is a particular kind of tree, and it's very easy to see this relationship in a path. In a path, the number of edges is exactly one less than the number of vertices. The other property of trees that we discovered was that there is a unique path between every pair of vertices. So because a tree is connected, we know there is a path between any two pairs of vertices. But for a tree, that path is unique. So now let's just do a warm-up example where we find all trees on 5 vertices. We'll look for all the trees on 5 vertices. Now for a tree on 5 vertices, we know there's going to have to be some leaves, at least 2 leaves. But what about the degree of the other vertices? Well, the degree of the other vertices could be a maximum degree of 2. Maybe there's a vertex of degree 3 or a vertex of degree 4. We can use that to try to enumerate or count these trees, or at least list them. So in the first case, I'll assume that all vertices have degree 2 or less. In that case, it's going to be a path. So there is our graph. Every vertex has degree 2 or less. We have 2 leaves of degree 1 and then 3 of the intermediate vertices that have degree 2. We could also have a vertex of degree 3. That could be our maximum degree. And so we have a vertex that looks like this with another 3 hanging off it. So that takes care of 4 vertices. Now we have a 5th vertex to add in. How could I add it in? Well, I can't add it in with an edge connected to that one because it would make this vertex have degree 4. And I'm assuming the way I'm listing these is that I'm looking at a graph or a tree with a maximum degree of 3. And so what that means is the other vertex, I can either add it in connected to that, or to that one, or to that one. But all of those are isomorphic, so I'll just draw one of them. I could have a vertex of degree 4. So that means our underlying graph would look like this. And that's used up all 5 of the vertices. And so we're done. There are 3 trees with 5 vertices, and we've listed them all. A couple of things we can observe about trees in general is that removing an edge, what does it do? It disconnects the tree. So removing an edge from a tree disconnects it. So we can see that from our examples above. If I remove an edge, that disconnects it into an isolated vertex and a tree on 4 vertices, or I could remove another edge, say in this one, that one there, and it disconnects it into these 2 components. In general, if we remove an edge from any tree, it's going to disconnect it. Now you may say, why is that the case? We can see it for our pictures up above, but why is that true in general? Well, let's imagine what happens when we remove an edge from a tree. What changes? Do we introduce a cycle? No, we don't introduce a cycle. If I remove an edge from a tree, it still contains no cycles. So is the result a tree? Well, if it was a tree, if I removed an edge and the resulting graph was a tree, then it would have to have this relationship. The number of vertices would have to be the number of edges plus 1. But I already knew that the original graph had that relationship. When I remove an edge, I don't change the size of the vertex set. I change the size of the edge set. I drop it by 1. So this equation would no longer hold. So I have a graph with no cycles for which this equation no longer holds. So it can't be a tree. So I have a graph with no cycles that cannot be a tree. So therefore it couldn't be connected. Because if it was connected, and contain no cycles, it would be a tree. So I have a graph that contains no cycles, and therefore it can't be connected. Otherwise it would be a tree, and therefore it would satisfy this equation, but we know it doesn't, because removing an edge broke that equation. So that means it must be disconnected. So in short, removing an edge from a tree in general, it'll disconnect it. What about if we add an edge? Adding an edge to a tree, what happens there? Well, it would create a cycle. And that's the same idea. So if I start with a tree and I add an edge to it, it can no longer be a tree because it wouldn't satisfy this relationship anymore. So if it's a graph that is not a tree, then what has to go wrong? Well, it's connected because all I'm doing is adding an edge to a connected graph. So it would be connected. And therefore the thing that would go wrong is that it could no longer not contain a cycle. And therefore it must have a cycle. So removing an edge from a tree disconnects it, adding an edge to a tree creates a cycle. So we'll now get to our main theorem about trees. This is our characterization of trees. The following statements are equivalent. That means if any one of them holds, they all hold. The first one says G is a tree. It's connected and acyclic. So if G is a tree, then each of these has to hold as well. It must be connected. The number of vertices must be one more than the number of edges. It must have no cycles, and the number of vertices must be one more than the number of edges. And there must be a unique path between every pair of vertices in G. So we already know that if 1 is true, then so is 2, so is 3, and so are 4. But what this theorem is saying that if 2, 3, or 4 are true, then 1 must also be true. It must be a tree. So these are different ways of characterizing what a tree is. A tree is a connected graph that has no cycles. Or we could say a tree is a connected graph with this relationship on its vertices and edges. Or we can say a tree is a graph that contains no cycle with this relationship between its vertex set and its edge set. Or we can say that a graph is a tree if there is a unique path between every pair of vertices in G. And so that's what we're going to prove. We're going to prove that these are equivalent by showing the following. So we will prove that condition 1 implies condition 2, condition 2 implies condition 3, condition 3 implies condition 1, and then we'll also show that 1 and 4 are equivalent. We've done most of the work already. This is really just bringing our previous ideas all together in one theorem. Let's go ahead and prove that 1 implies 2. So suppose G is connected and has no cycle. In other words, G is a tree. Then what we get from that is that G is connected. That's just a restatement of the hypothesis. And we know that the size of the vertex is equal to the size of the edge set plus 1. That was theorem 7.1.3. And so we're done. 1 implies 2. Now, how do we know that 2 implies 3? So we'll assume the hypothesis for 2. So suppose G is connected and the size of the vertex set is the size of the edge set plus 1. We want to show then that it contains no cycles. So the way we're going to do that is I'm not going to set it up this way, but this is good to think about in advance before we start to do the proof, is that suppose it did contain a cycle. Then what has to happen? Well, if it contains a cycle, I can pick an edge on that cycle and remove it, and I still have a graph that's connected. The problem is I will no longer have this relationship because my edge set will have dropped by 1. But that's fine, because if there's still another cycle, I'll remove an edge. If there's another cycle, I'll remove an edge. So I keep removing edges until I get down to a place where it's still connected, but there's no more cycles to remove edges from. So now I have a graph that is still connected. It has no cycles, so it must be a tree. The problem is, if it's a tree, this is the relationship that it would have to satisfy. But every time I removed an edge, I would, well, after the first one, I've already broken this relationship. So if I removed an edge, it would have broken this relationship. So that means I couldn't have removed any edges, and therefore it would have not had a cycle to begin with. So the way I'm going to write that up, so that's sort of the big picture perspective, but the way I'm going to write it up is this way. Rather than say remove an edge and then check again, remove an edge and check again, I will just let E1 up to EK be the biggest collection of edges that I can remove from my graph and have it still be connected. So let this set be a maximal collection of edges so that G, take away these edges, is connected. And if I remove any other edge, then the graph will then become disconnected. So in other words, how would I have found this? Or how would I have collected together these edges? EI is on a cycle in G, take away all the prior edges, E1 up to EI minus 1. So that's how I would have collected this set together. I would have said, oh, if G contains a cycle, remove an edge from that cycle. If it still contains a cycle, remove the next edge. If it still contains a cycle, remove another edge. If it still contains a cycle, and so on, down to remove an edge EK. Now it no longer contains a cycle. And I haven't disconnected the graph at all. I just keep removing edges from cycles, and the underlying graph will therefore remain connected. So now what can I conclude from this? Well, I'd like to show that I couldn't have actually done the process at all, that K is actually 0. And so let's see if we can show that. So then, G, take away E1 up to EK is what? Well, I've only removed edges on cycles, so I haven't disconnected it. So this is still a connected graph. And what else? It's a connected graph which now has no cycles because I've removed all the edges on all the cycles. So it is connected and acyclic. In other words, it is a tree. So if it's a tree, then what do we get? Therefore, the number of vertices is equal to the number of edges in that graph. Well, how many edges are there? Well, this is the number of edges in G, and I've removed K of them. So that's how many edges there are on G, take away E1 through EK. And so because that is a tree, it means that we have this relationship. The number of vertices is exactly equal to the number of edges plus 1. The problem is, in this original graph, we had this relationship, that the size of the vertex set was equal to the size of the edge set plus 1. So in other words, I also have that this is equal to E plus 1. And in order for E plus 1 to equal to E minus K plus 1, this means that K has to be 0. Okay, so what does that mean? It means the maximal collection of edges that I'm allowed to remove and have it still be connected is 0. I can't remove any edge and have it still be connected. And so therefore, since I can't remove an edge and have it still be connected, it must not have had any cycles to begin with. So G is acyclic. It didn't have any cycles to begin with. And the number of vertices is equal to the number of edges plus 1. So the reason I've written it in that way as our conclusion is because that's what I'm trying to prove. If it's connected and the number of vertices is equal to the number of edges plus 1, then it must have no cycle and the number of vertices is equal to the number of edges plus 1. And that's what we've just shown here, is that it is acyclic or has no cycle and the number of vertices equal to the number of edges plus 1. So we've just proven that 2 implies 3. Now we want to show that 3 implies 1. So we will suppose G has no cycle and the number of vertices equal to the number of edges plus 1. In order to prove that 1 is true, I just need to show that it is connected. So why must it be connected? Well, since it contains no cycle, then it must be a forest. So G is a forest with, let's say, k components for some or where k is greater than or equal to 1. But because it's a forest with k components, then we know that the number of vertices, that's equal to the number of edges plus k. And that's by theorem 7.1.3. So for a forest with k components, the number of vertices is k more than the number of edges. But we also know, by hypothesis, that the number of vertices is e plus 1. That's by our hypothesis. So it's written right here. And therefore, that tells us that k is equal to 1. So there must be one component, and that means it's connected. So that implies that G is connected and has no cycle, because that was, again, one of our assumptions. It has no cycle. So G is connected and has no cycle, and therefore the conditions for 1 are satisfied. G is a tree. So we've just shown that 1 implies 2, 2 implies 3, and 3 implies 1. Now we're ready to show 1 implies 4, and 4 implies 1. So remember, 4 was there is a unique path between any two pairs of vertices. And condition 1 is that G is a tree. So we've actually already proven this. This is theorem 7.1.2 in lecture 28. We've already shown that if our graph is a tree, then there is a unique path between any two vertices. So now we'll show the opposite. If there is a unique path between any two vertices, then our graph must be a tree. So we're going to suppose G has the property that there is a unique path between any two vertices. And now we want to show that it's a tree. So we need to show that it is connected and contains no cycles. Well, this already tells me that it's connected, because this tells me actually an even stronger condition. It tells me there's a unique path between any two vertices. But even if I ignore the word unique, it says that G has the property that there is a path between any two vertices. So G is connected. G is clearly connected. So I have to say clearly in this case, because this is really just, it tells me right there it's connected. It tells me G has the property that there is a path between any two vertices. So it is connected. G is connected. Why is there no cycle? Well, suppose G has a cycle. Then it would look something like this. Maybe I'll pick one edge on that cycle, and then it would go around like this. There'd be some more vertices, and so on around. So there's a cycle. What we have is that this gives us two paths between A and B. So there's this path, let's call it P1 from A to B, and then there's this path that goes around the opposite way around the cycle, and that's P2. So suppose G has a cycle, then there are two paths from A to B, and that's a contradiction. So these arrows hitting each other are denoting a contradiction, because our hypothesis says that there is a unique path between any two vertices. So if there was a cycle, that would contradict the hypothesis. So therefore, G has no cycle. And so we have that G is connected and it has no cycles. So we can conclude then, therefore, G is a tree. And so 1 is satisfied. And there we go. We've proven all of the things we needed to prove. We proved that 1, 2, 3, and 4 are all equivalent to each other. So that characterizes a tree. A tree is a connected acyclic graph, but we can use any of those other properties as well to characterize trees. So the next half of this lecture is going to get into a special kind of tree known as a rooted tree.